You may be seated. Esteemed PhD candidate, the doctorate board of this university, represented by us, has read your PhD thesis and the propositions that go with it, and we are ready to hear you defend it. Please take your seat. We start the defense with the members of your assessment committee, and in particular with Professor Alegre from the University of Lyon in Spain now. Please go ahead, Professor Alegre.
Okay, good afternoon, everyone. Thank you for the invitation, for being a member of this committee. Esteemed candidate, I read your thesis thoroughly and I like it, what you have done. I realized that you proposed three main contributions in your thesis. One of them was the use of crossfire for classification of radio galactic morphology. And you claim that you achieve a higher accuracy and lower computational cost compared to deep CNNs. I would like to talk with you about this as one of the points that I want that you elaborate a little bit more about that. And you have another two contributions. One is the use of also crossfire as combined with deep hasing for image retrieval. That is also interesting, and it's a descriptor for efficient accuracy retrieval. And the third contribution was in the anomaly detection. And if I have time, I also would like to ask you, could be one or two questions about that. My main interest is that you explain a little bit why you do the comparison, how to do the comparison in first term with the CNNs. You claim that, you present results where you show results where you compare your contribution with DenseNet 161. And my impression is that it's a little bit heavy architecture. So as you are claiming that crossfire is lighter, more efficient, I would like to know why did you choose this architecture for doing your experimentation and for comparing with crossfire? If you want to explain to me, I will appreciate it.
Dear highly learned opponent, thank you very much for your kind comments. I would like to respond to your questions. Yes, for this particular work, we use different architectures, as you correctly highlighted. So we use DenseNet, we use group equivalent convolution neural networks for different, and also MLP, as you said. One of the reasons, or what inspired us to use, for instance, DenseNet as part of the workflow. So for the data set that we picked, so when we first did the literature review, forms the first chapter. So one of the things was to identify a data set that would be very relevant to help us prove what the ideas that we have for convolution, for crossfire filters and see how it would perform. So once we identified the data set, which was quite relevant and representative within the scope of our study, the state of the art for that specific data set was actually DenseNet. And if you check on chapter 2, that is the first experiment that we do a comparison and see, can we outperform or can we compare actually? The aim was not specifically to outperform that, because we realized that the architecture that was used is quite, with very high number of layers, as you said, 161, which is quite deep. And this leads to, of course, overfitting as one of the key challenges. So once we identified that, then we thought, okay, within the space of astronomy, the data is quite large. So utilizing such an architecture which is quite deep and the data sets are massive, it doesn't make a lot of logical sense, especially considering the computational cost. So could we get an approach that is lightweight, that is innovative, and countering that approach and get competitive results, either give similar results or even better? So that was the main motivation for choosing that, or choice of the architectures. Yes.
And did you consider other architectures lighter and also high efficient, like ResNet 18, for example, or MobileNet? I imagine that you consider them as well.
Yeah.
So
yes.
Why did you choose DenseNet? Or probably you tested some of them. So if you did it, could you tell us the results or what happens there?
Yeah, thank you, the highly learned opponent. So specifically the DenseNet, like for chapter 2, the choice of DenseNet was not actually ours. It was for the reference paper that we used as a benchmark because it had the state of the art. So ours was actually to identify another algorithm or another approach that is lightweight and can give us competitive results. So, and I remember during the experimentation, our very first test, we actually explored AlexNet. We explored VGG network. We also explored ResNet 50. And then along the same lines, that's where Crossfire was also within the line, and the performance for Crossfire was quite tremendous. And also considering the other architectures, because most of them were actually considering the transfer learning approach. So definitely the layers were a bit high, and also the performance was quite a bit lower compared to the DenseNet. So that is why they didn't warrant to be included in the results when we are publishing the article. So, and the reason for this specifically is, if you look one of the, I think it's diagram 1 in chapter 2, you see that the different classes that we have are very close. So some of the galaxies they share a lot of similarities. So it is not easy to get good representation that are separable. So for this particular case, we needed an approach that would be would be able to learn the intricacy and the complexities of the different morphologies across the galaxy classes that we have, which is a very common problem within the astronomy space, because the galaxies tend to be very similar in a way, and that's why now most astronomers choose to use the manual approach as opposed to doing it in an automatic fashion. I hope that answers your question.
Thank you for your answer. Yes, and also related to your answer, as you mentioned, the number of images is large in this field, and you use a small data set for testing. But I miss that you didn't mention or consider to use transformers for doing your experimentation. And the reasons are because, of course, with the small data set as the one that you use for your testing, probably Crossfire and other CNN-based architectures could perform better. But even you have lighter versions like DIT or SwingTiny versions of transformers that could be used, and also they work well in a small data set. So I would like to know what crossed your mind when you consider, because I imagine that you consider to use transformers for this problem, and what happens there?
Yeah. Thank you very much for your follow-up question. And to answer that, I will retaliate on something that I mentioned earlier. is that when we were making a choice of our model, we had an already state-of-the-art DenseNet algorithm, which is a heavyweight. And our main consideration was actually to look at the scalability of the approach that we want to put into practical use and see how the performance would be. So within the same line, yes, as you mentioned correctly, transformers are actually like vision transformers are specifically providing state-of-the-art performance, though not with like significant additions, because I'm working with transformer at the moment where I'm working. But one of the things is, so given the premise that we are starting to work from, we want a lightweight, so that by itself, by design, eliminates like using a very heavyweight approach, because our aim was to utilize as minimum number of flops as possible and still get the similar performance. So that is why it was brought into consideration. We had to drop it.
And I one last question, if it is allowed. I think that the approach is right, but if I am not wrong, the data set in this field are very large. So imagine that we have a lot of variations in morphology, and they are subtle. And in that case, probably with Crossfire, you could have problems to recover, to take these morphology variations. So you don't consider that using a transformer-based approach could be better for learning different patterns that are not pre-considered in your approach using Crossfire?
Please be brief in your answer.
Okay. Thank you very much. As you mentioned correctly, yes, the slight variations could be handled well within transformer context. However, within the Crossfire approach, we also try to be innovative in the design and implementation process. So what we try to make sure is we use higher number of filters, and this is like the number of prototype examples, which would also compare with the different variations within the database. So within the Crossfire approach, ideally, the more type of prototypes within a class you provide, then it means you're getting a feature map that is also more representative. So ideally, if you look at the performance, especially for the first paper, you realize we use almost around, if I remember correctly, 372 filters. So the more filters you use, the more we are able to capture the intricacies. Thank you.
I have no more time, but thank you very much for your answer, esteemed candidate.
Thank you.
The opposition is continued by another member of your assessment committee, Professor Bunte.
Dear candidate, I was really happy to see the thesis that in astronomy there's also alternatives to deep learning to see that can be used on image data. So I was happy to read that. My first question is related to the stelling number 6. So I would like to ask one of the paranymphs to read number 6.
Hello. Hashing Crossfire descriptors into compact binary codes enables scalable, morphology-aware similarity search across large radio images archives.
Thank you very much. So my question for this is, it was interesting for me to see that hashing is used basically as a code word representation from the latent representation that you got from your Crossfire architectures. So I was wondering, how did you come to this choice? Because hashing is dependent on the hash function, on the hash size, and it's heavily dependent on the data distribution that you give in. Your latent representation is, however, something that you do not steer in any way. So have you ever checked what the data distribution of the latent representation, what the effect is on your hashing?
Yep, thank you, dear highly learned opponent. Thank you very much for your question. So the reason why we thought, and this was actually a very careful thought and deliberation on the choice of it, is because our choice of the design was actually the fact that when you're dealing with hashing functions, so we had to learn the representations in a way that is an end-to-end fashion. And the way we particularly learned it was to make sure that the end representation are quite compact. And when I say compact, what I mean is we ensured that the output of each image is actually like very close to binary form, like push it and make sure that the end product is either very close to -1 or +1. So this ensured that and this is during the learning process in the end-to-end fashion. That's why we use actually MLP in that particular case. So, what this means at the end is that the model that we are learning, we try to also customize our loss function to make sure that it helps us to push those values in a way that, they're very close to zeros and one. And then now the whole process helps a lot in the post hoc analysis. And what I mean by post hoc element is because after we have learned the model, we now do the encoding to zeros and one. So when you convert them now by thresholding to 0 and 1, the quantization error is quite minimal. And this helps a lot because now when you come to the database, it doesn't matter you have millions of images. So each image will be encoded to a 0 and 1. And this is basically the language of computers. So when you have a very large database with millions of that, but all the images are encoded to very compact representations of 0 and 1, when you come to the image retrieval process, it's super fast because we are just comparing the binaries between the query image and the whole database. So the process becomes super fast compared to other approaches that are used there because they keep their values in real values, which, that creates a computational burden compared to approach. So in fact, within the image retrieval space, hashing representation is actually like the state of the art that is most preferred.
And did you check for the hashes that are used? Because you also have highly imbalanced data sets. So some classes of galaxies are just much more frequent than others. In particular, the faint ones, we barely know any. So how much the capacity of the hash was actually used?
Yeah, so for that particular case, what you said is very correct. The different galaxies are quite imbalanced, and even this is also seen within the data set that we use. We have one that has higher majority. But then when we were designing our model, we also tried to apply strategies that would help us take advantage of, that would help to at least mitigate the problem of class imbalance, like upsampling the lower class, for instance, so that at least the majority class is not overrepresented, and also the minority class is not also underrepresented. So we try to make sure, like during the learning process, we take care of that specifically. And if you look at the performance of the hashing, you see for all the classes that we have for our crossfire approach, almost all the accuracy for each specific class is actually 90. All of them is 90.1. So we try to make sure that that is already captured, and the performance by itself shows, we tried to achieve that to a good extent.
Thank you. But the hashes themselves, did you ever vary the size of the hashes and see what the effect is? So, I mean, we know from networks that basically they're having rather similar latent output, so they're not using all the space that is at their disposal. So my hypothesis would be that as soon as you have the capacity basically large enough, that you have diminishing returns, that increasing the hash doesn't deliver you much. Have you ever checked what is kind of the minimum that you need, and if it's dependent on the size of the images or on the catalog where the images are from, the survey? What has the highest effect on the performance?
Thank you very much for your question. Indeed, that is one of the things that we actually had a reflection on. And if you look at, I think this is page 74, so we had to try also and vary that, and like empirically do an experiment on that, because one of also an objective, as you said earlier, is also on checking on scalability and making sure that we're using as much as possible minimum computation to get good results. So what we did for that specific example, so we used different levels of hash function of the length of the binary code. And in this case, we used like from 16 to around 80. In this case, so we had those experiments which were run separately, and then from there we compared. And if you look at that, as you said, so as you start from when the hash function is quite low, it's quite energy efficient, but then the performance is quite low. It's like similar to classification typically. But as you increase, it gets to a point that the returns, as you said, are quite diminishing. And then, interesting enough for this case, when it gets to around 80, it starts to tank. So for us, our base was actually 72. And this was from empirical experiments. However, if you note, we also noted that at around 50, just from the plotting, we realized that will be the optimal if we still want to save on the efficiency in computation. I hope that answers your question.
Thank you. I see that I have to
Thank you.
do the questioning later. Continuing. Thank you.
Thank you. Then we continue the opposition with yet another member of your assessment committee, Professor Kamper from Stellenbosch University.
Good afternoon, everyone. Thanks a lot for having me part of this defense. Geachte promovendes, I want to start by just thanking you for the thesis. I thought it was quite short and to the point, but it was still more than sufficient to provide enough context for the work and to appreciate the contributions of the work. So thank you for that. I appreciated the images a lot. It made it an entertaining read. And then ultimately, I think the proposed method worked really well in terms of efficiency and accuracy, and that's really commendable. I'll just start by thinking about some of the more critical points, and I'll build off some of the stuff that the first opponent mentioned. I wanted to ask about the data set that you use. You promote this approach, Crossfire, as something that's very efficient, but you use a very small data set to validate the approach on, also to compare to previous work. But my question is, how representative is this data set? How toy is the data? How will it resemble something if you actually move to a real world case with a much larger data set?
Yeah, thank you, dear highly learned opponent. Thank you very much for your question. So I would actually like to address your question. So the data set that we used was quite small. As you see, it's in the magnitude of 1,000. And that is typical within the astronomy space, because I was surprised, and during the literature review, I kind of had to explore all type of data sets that are labeled that we could find. And we were hoping to have as large data set, because within the machine learning and deep learning space, you want to have as much data so that you can learn your models effectively, and it's also much more interesting. However, within the space, the labeled data sets are quite small. It's now that we are progressively having more and larger data sets. Unfortunately, my PhD is already has come to an end for that. So to answer your question, how representative was this data? To be honest, considering all the galaxies that are available, especially considering the FR, the Fanarov relay classification scheme, our data set is quite representative. If you look at the table summary that we provide in chapter 2, you find that some of the data sets, like the mirror base, they kind of have only 2 galaxy classes, that is the FR1 off and FR2. But for our case, we wanted to pick a data set that is more diverse, and it contained 4 classes. This is FR1, the compact. The compact is always the majority within the galaxy space. And then we have the FR2 and the bent. So typically within the data space, those are the highest, let's say 90% or more, actually 95% of the composition of that. There was only one class that is not captured in this particular case, and these galaxies are very rare. This will be the X ring, and you have them, the ones that are very circular in nature, and those ones are considered to be anomalous because they are very few in number or in count. However, within our experiments, we also made sure that we are capturing them and utilizing them, and that is in the last chapter. So at least within our end-to-end, from chapter 1 to chapter 4 within our work, we made sure that our algorithm or our Crossfire is at least cutting across all the, typically all the galaxies that could be found or we expect to have. Yes, I hope that answers your question.
Yeah, thank you. It's tricky to make findings, big findings, and even a whole field can make wrong findings if your data isn't representative. So I think it's an important thing to consider. My second question actually relates to something that the second opponent asked. but it's a little bit more in depth. As I understand it, this is about the hashing function as well. As I understand it, you do binarization kind of implicitly in the network by pushing the values to -1 and 1. I have two questions. The one is there a way to be more explicit within the neural network training to force it to be binary? And then secondly, is there actually ideally a way to train the hash function together with the rest of the neural network? Is there actually a way for the neural network to be aware of what will happen at inference time when you hash, and that it can incorporate that when it's learning its latent representations?
Thank you very much for your follow-up question. And the answer to that is yes. We can implicitly learn that, and this is courtesy of the loss function. If you look at page 69, so we adapted a loss function that should implicitly apply that. And you find that, so it has three components. The first component and the second one are mainly helping in making their presentations separable. That is, if they are similar to a specific class, or if it is not similar, then it should be penalized. But then the last component specifically is aimed at making the representations that we are learning binary-like. We don't want the values to be between close to 0, like 0.1 or 0.2, of course, depending on the size of the hash function. But we want them to be pushed to the end. If you look at, if you look at how the representation look like in a diagram that we show in figure 4.8, if you look at the drawings, it shows like a bimodal structure, which shows that we effectively, and this is learned ideally implicitly within the neural network pipeline. So all the values are pushed to the end, that either -1, and as I said earlier, it helps in reducing the quantization error specifically. So when you're binarizing, you're not losing any information from the galaxy type. Yeah, so the answer, I hope that answers your question.
Yes, thank you. My last question, which I'll just ask briefly, is also about the different model architectures for the neural networks that you compare to the CNN model, or even transformers or something like that. I wanted to know, because often you start with a model that's actually pre-trained for image classification. So if you can't, it's very difficult, especially on your data set size, to take a model, maybe the state-of-the-art big transformer model, you won't be able to train it on the sizes of data here. So you will start by using a pre-trained model trained for general image classification. And I wanted to know, how well does the CNN filters actually transfer across domains? If you've trained one model on, classifying between dogs and cats, does it actually still help you when you're doing this type of radio astronomy data classification?
Sorry, I don't know if I got your question clearly. Do you ask how the Crossfire approach will transfer?
No, I'm asking about neural networks. So if you have a state-of-the-art image classification neural network, the biggest transformer that we can find right now, that model hasn't seen any radio astronomy data. It's seen other types of data. My question is, does the other types of data, does that actually help you when you move to this new domain of radio astronomy? Does the filters actually transfer across domains?
Thank you very much for your question. I think I use chapter 4 to answer your question. So if you look at chapter 4 part A, we have two publications for that case, and chapter 4 part A should address that question. So we use weights from a larger data sets, and this was ImageNet specifically. And the aim was actually to do a transfer learning and adapt it within the radio astronomical space. And from this specific experiment, I would want to make my inference on how to answer that. So when we directly apply that and make the learned algorithm not to just be feature extractor as opposed to also like updating the weights a bit, the performance was a bit low, which meant that the land representation outside the astronomical space was good because the performance was not that bad, but it was not equating to the state of the art. However, if the way we updated it to make sure that we still take advantage of the land features, not explicit within the astronomy space, we kind of like did a slight update on the weights. So we did like a tuning of around like those 10 epochs a bit, so that we're adapting the weights within the astronomy space, and then from that freeze the weights like the backbone, and then now update or fine tune within the astronomical space, and that worked pretty well, giving good results as presented within that chapter. So my inference for that they are good enough to be applied, but then it's good to like make sure we update the weights because they are a bit far, because the structures are completely, well, this is from space and this is from Earth, so it's a bit different, yeah.
Thank you, geachte promovendes. That's all my questions.
Thank you.
Then we continue the opposition here in the room with Professor Morganti from the Kaptein Institute.
Thank you. Esteemed candidate, I read with interest, a lot of interest, your thesis. Well done.
Thank you.
I've done some work in a similar field that, as you say, is an hot topic, and indeed it is, considering the survey appearing and coming. But I did the work as an observer, so coming from the other position and perspective. And so I would like to continue the discussion about the sample that you use in the morphology. And so I was, in a way, surprised. You mentioned, you explained to the previous professor the question about the sample that you use. Is a sample, at least part of it, come from Proctor, one of the, that is taken from a VLA survey, 30 years old, I would say. Not very deep survey and relatively high resolution. So this survey first is known to be sensitive only to, or mostly to, compact structure. So would miss out all the extended emission that a source can have.
True.
And we have seen this with the LOFAR, with Meerkat. Meerkat is showing wonderful, beautiful structure of radio galaxy. So I understand why you did. You wanted the sample already classified, but I was expecting at least a comment about how do you think your method would work if instead you would apply to much deeper. So survey image where you have a lot of extended structure, where your scheme FR1, FR2 that you show in figure 2.4 is a bit, it's a cartoon. It's real life sometimes is more complicated than that. So I was just expecting some comment on this, but maybe now is the opportunity.
True. Dear highly learned opponent, thank you very much for your question. Actually, that's something that we took with a lot of interest to do that. And the aim of the last chapter for anomaly detection, we were actually in process of utilizing the MICAT dataset from colleagues from a university within South Africa. But due to few challenges, the data was not published yet as a paper. So we were not able to specifically utilize that, like a more recent data set. So we had to opt for an already existing data set for that. So, but to comment on that, yes, the data set is old, but it helped us to benchmark and see how COSFIRE applies on the dataset that is widely used. How COSFIRE or how methodology would apply for more recent datasets. So this would be my speculation, and this is also informed on how it performs with outside astronomy, because the approach has also been experimented widely within other domains. So given that LOFAR data, for instance, it captures more diffuse components, it's higher resolution as well. The performance I would hypothesize would be better because By design, COSFI approach is designed to capture the structural morphology of the given prototype image. So if we have a higher resolution or even diffuse, so the components will be more clearer, which means that we are able to pick the salient features even in more detail. Because for this case, since this, and then, well, ideally, the components will be more resolved. So for this case, we had challenges of the fact that it's not very resolved, some components, so there's a lot of confusion between one galaxy to the other. So when you have higher resolution, of course, I imagine we would have more details that we can encode within the COSFI configuration process. And the more details we have, the more the approach will be able to distinct different morphological classes. Yes, I hope that answers your question.
Okay, so my point in a way is that going to the chapter 5 that I was, of course, very interested to see.
Sure.
I kind of disagree with one of your statements that radio sources with anomalies are a minority. So forget about the compact. Compact, who cares? Compact are compact. But for the extended one, and compact are a majority actually, but okay, we forget. But for the extended one, the pure FR1 and FR2 like you draw
Yes.
are maybe also a minority. The rest are kind of messy. Sometimes they have the hot spot in the middle. Sometimes they have some tails. So, and there is more than the egg shape or the circle that you focus on. So if you really want to discover something new, would you be able to do with your, because Van O'Reilly 1 and 2 had been studied.
Yeah.
I mean, Mingo also did, so I was puzzled why you didn't use, for example, that sample. But the rest, the strange, would you be able to find them without starting already with a kind of preconcept that either they should X-shape or a circle, or FR1 and FR2? So,
yeah.
The rest.
Yeah, thank you very much for your question. I would suspect that we would be able to do that because, especially for the chapter 5, the last chapter, because the design of the methodology is to have, assuming we already know what we consider as normal, or the frequent ones that we are used to, is to configure the approach such that it's able to capture and understand them easily. So if you have the morphology of a non-galaxy, then it's easy to have, it will be configured in such a way that the responses that you obtain from that will be very high. And whenever you have a structure that is quite off, which is very complex with jets that do not exist within the typical ones, then the response will be very minimal because as we apply the configuration process, we basically try to pick the structural appearance of a specific, and then we try to get like almost exact or replicas of what you already have. So whenever you have something that is off completely, then the responses will be very low, which means, well, it should be easy typically too, because the responses for those that are completely anomalous will be very low, because the COSFI was not
maybe
trained.
Among the off, there are some very interesting sources that
probably. But this would be very interesting to explore and see how it would apply.
Yeah.
Thank you.
Thank you.
We continue the opposition with Dr. Wilkinson.
Geachte promovendus, esteemed candidate, I read the thesis with a lot of joy. I'm a computer scientist, but I do have some astronomy background, so this mix fits me perfectly. And I was also very interested in the use of rotation invariance. That's something that we've been working on as well in a different context, where you basically say by adding rotated versions of your filters, you get your rotation invariance, and you can, of course, arbitrarily closely approximate perfect rotation invariance. But I was wondering, did you consider using scale invariance? Because given, you know, objects can appear at all sorts of scales, how would you address that?
Dear highly learned opponent, thank you very much for your question. Yes, as you say, we explicitly ensure that we've encoded information for rotation invariance, and this was very helpful to help us capture galaxies in case there's a bit of, well, the telescope captured it from a different line of sight. But as you said, for the scale invariance, we did not address it for this particular case, and this is for simple reason is because within the images that we are using, they kind of are within the same space. The scale is not too different, looking at how the structure or the morphology was appearing. So it did not necessitate us to include scale invariance. But this would definitely was something that would have considered if you wanted to do a cross survey or apply to other higher resolution, for instance, because the galaxy will be more resolved. Some of them will be extended and definitely would want to, well, to be larger than normal. So having a fixed scale parameter, which is the Gaussian for the Gaussian filter that we used, would not have been sufficient enough to capture that. So how to address that in now cases that this will be applied would be in a similar fashion to how we utilized rotation invariance. So for the sigma parameter, we would also now use different values of sigma, and then which would now be adequately capture the different variation in size and scale, both small. So for smaller galaxies, if you want, we'll make sure we have within the different variations a smaller parameter value of Gaussian and or the kernel size. And also for if you want to capture the larger ones, we would have a larger value of the kernel size of the Gaussian. So this is typically, so within that is just encoding, adding a new layer from the baseline crossfire filter, which you use to adapt to that.
But I mean, at a certain point, you get rather a combinatorial explosion of, if you have to have scale invariance and rotation invariance, how many different variations of the filter do you effectively use?
Yeah, thank you very much for your question. So we won't have an explosion typically, because ideally, I think this would be answered by one of the experiments that we did to see how the number of tuples and how they increase as you do, you introduce, let's say, rotation invariance. I would use that for, this is in figure 3.6. So we would observe when you introduce rotation invariance, we have an increase in the number of filters that we use. However, the increase is sublinear, so it's not like linear or to a large scale. So if we introduce now rotation on top scale invariance, then that would mean there will be an increase but not an explosion. And the reason behind this is because the tuples, as you keep on adding much variation like rotation and scale, there's a lot of shared values. So as you increase the number of shared, so they kind of, you want to reduce redundancy, so we only pick the unique ones. And then we also store like the tuples, so we only load them to apply when performing the, let's say, the application part. So the number would, number of operation would increase, but not exponentially, not linear. It is in a sublinear, and this is already experimented.
But have you considered, perhaps there are other ways, of course, of detection of objects, one of which we've been developing here called max-tree objects, which looks at connected structures that can't be assigned to being noise. And there you get, of course, your scale can be very easily measured in the terms of the area of the object or the bounding box size. But there what is done is your scale and rotation invariance can be achieved by actually measuring certain properties. Would something like, if you say already know the scale of your object, would you then perhaps not have to search through a parameter space as much with the Crossfire, that you can combine this? I invite you to speculate.
Sorry, I lost track a bit.
Okay.
Sorry, do you mind repeating?
Okay, so a different way of detecting sources in astronomical images is using basically so-called connected filters that look for connected components at all threshold sets of the image. And by detecting structures that you can say, I can't explain that by noise, this must be an object of some kind, you can, this is mainly done in the optical. We've done some experiments in the radio, and there's still quite a bit of work to be done there. It may well be that you have not seen this, but these are, their scale invariance and rotation invariance are basically extracted because of properties that you measure, like elongation is a scale invariant, but also rotation invariant measure. And this gives us information about the morphology. Whereas you're looking more explicitly at certain patterns, which our method is more or less blind to. Would it be possible perhaps to combine this in some way, that you say, well, if I know the area, then I don't have to test a whole lot of different filters because I know that it's a certain size class. Would that perhaps help in keeping the complexity down?
Yeah, I think I would say yes, but I don't want to speculate a lot because of, the limited, But I think it would help for sure.
Okay, then one last question, I expect at least, is you talk in chapter 3 about classification, and it was alleged already that there is something to be said against the particular classes that are used. Is classification, because I've seen in optical data that, okay, you've got the Hubble tuning fork diagram which says, oh, this is a spiral, this is a barred spiral, and if you really look at the things in practice, you see that there's a whole zoo of things, a whole continuum. So would some form of regression perhaps be better than a classification in this case? What are your thoughts on that?
I think, so for this particular case, as you say, classification would definitely be interesting because as we look at the population of the galaxies, they're quite vast and diverse, but then they also share a lot of similarities. And as we look at maybe for what we experimented a bit and what I could see is when we did like just going beyond the classification, we did image retrieval because it's a hybrid of, let's say, classification. And indeed is where we get like, okay, this galaxy is classified in this, to belong to this class. And doing image retrieval was like, okay, yes, it's classified within, but can we also have a set of galaxies that are also very close to this, which would typically be classified within the same class, and see how do they vary. It seemed very interesting because the top galaxies would be very close.
Thank you.
Thank you.
The doctorate board will withdraw for some time to consider its decision.
Thank you.
And you may be seated. Esteemed PhD candidate, the doctorate board of this university, represented by us, after reading your PhD thesis and the accompanying propositions, and after hearing you defend it, has decided to award you the PhD degree at the University of Groningen, which you desire, and this being a double degree, also the one at University of Stellenbosch. Your primary supervisor, Professor Azopardi, is authorized to award you this honor in the customary fashion.
I am happy to accept the task assigned to me by the Rector Magnificus. However, before performing this task, I would like to address a few personal words to you. Dear Stephen, it is a great pleasure and honor to stand here today and celebrate your PhD journey. This moment marks the culmination of years of dedication, resilience, and intellectual curiosity. Our story began 5 years ago during an academic leadership course I attended. That same week, the University of Groningen announced its list of 10 strategic partner universities, one of which was Stellenbosch. During a coffee break, I met Stefan Weinholz from Astron, who mentioned his professorship appointment at Stellenbosch. That conversation sparked an idea. Well, Stefan connected me with Trienko Grobler and Dirk de Villers, whose enthusiasm and financial support laid the foundation for this collaboration. From the very beginning, the chemistry between our teams, I would say, was exceptional. The next step was to open the PhD position. We received over 100 applications, and after a rigorous selection process, the decision was unanimous. We had found the right candidate, and that candidate was you, Stephen. When you moved to Groningen, I was immediately struck by your positivity. Housing in Groningen is notoriously difficult, and you initially struggled to find accommodation. Yet you kept saying, well, I'm not worried, I will find a good place. And you did. That optimism and calm confidence have been hallmarks of your personality throughout the journey. You integrated seamlessly in our group and quickly became a valued colleague. Your research tackled one of the most pressing challenges in radio astronomy, how to analyze data efficiently for telescopes like LOFAR and the SCA and more. You developed the CARAT framework that combines efficiency, interpretability, and scalability. At its core, it is the crossfire filter approach, which you adapted to radio astronomy. It is rotation invariant, computationally frugal, and scientifically transparent. Your work addressed three critical tasks: morphological classification of radio galaxies, achieving state-of-the-art accuracy with 20 times fewer computations than DenseNet-based models; content-based image retrieval, enabling astronomers to find morphologically similar sources in archives; and anomaly detection, identifying rare and unusual radio galaxy morphologies using a semi-supervised approach. These contributions represent a paradigm shift towards sustainable and interpretable machine learning in astronomy. Your publications in high-impact venues, along with presentations in Japan and Sydney, attest to the impact of your work. And let us not forget the URSI Student Paper Award, a well-deserved recognition of your work. Something truly remarkable of your journey is that every paper you submitted was accepted after 1 or 2 rounds of revisions. No rejections. That is almost unheard of in academia. I hope you keep this strike going for as long as possible. But knowing your resilience, I am sure you will handle reviewer 2 with grace when the day inevitably comes. And remember, reviewer 2 doesn't only live in academia. They exist everywhere, disguised as project stakeholders, policy advisors, and even the occasional neighbor with helpful feedback. Beyond your academic achievements, you embraced life fully. You managed a double PhD between Groningen and Stellenbosch, navigated visa and housing challenges, and still found time to visit your family in Kenya regularly. And of course, you married Janet Mutuku, who is here with us today, a milestone that deserves its own applause. Your co-promoters, Stefan Weinholz, Trienko Grobler, and Dirk de Villers, describe you as a friendly, punctual, hardworking, and collaborative person. I would also add that you are resilient, adaptable, and deeply committed to excellence. Your personal qualities have shown through in many ways. One example is your caring nature. When I visited you in Stellenbosch, for example, at the end of my stay, I fell quite ill, actually. And you got me a malaria test kit to rule it out as soon as possible. Well, thankfully, the result was negative, but that thoughtful gesture speaks volumes about who you are. And then there is your resilience. I still remember your legendary patience with the Dutch healthcare system. What started as a simple dental issue turned into a masterclass in endurance. Delayed appointments and sleepless nights. If resilience were a metric in dentistry, you would have earned an extra qualification. Your success today is not only a testament to your talent and perseverance, but also to the power of collaboration. As an African saying goes, alone we go faster, but together we go farther. This PhD was a shared journey between Groningen, Stellenbosch, Astron, and your family, each step driven by collaboration and mutual trust. And since we started this joint venture, the relationship between the two universities has strengthened even further. Thanks to you, Stephen, there is now a path for others to follow. Finally, I would like to thank the entire supervision team, Dirk de Villers and Trienko Globler, who are following us online, Stefan Weinholz, and Dimka Karastajonova for her early involvement, and the Sub-Saharan African community who facilitated this project through Anita Veldmat. And now, as you embark on your next chapter as a data scientist at the United Nations High Commissioner for Refugees in Copenhagen, we know you will continue to make a difference, not only in science, but in the world. Stephen, we are proud of you, and I am sure your family in Kenya, including your parents, Patrick and Jane, are even prouder. And let me conclude with this. As a true Kenyan, you didn't just run the academic marathon, you sprinted to the finish line before your PhD contract even expired. I'm sure your compatriot legend Eliud Kipchoge would be proud of that pace. That's a record few can claim. Congrats, Stephen. Okay, we can all stand up. By virtue of the powers vested in us by Dutch law, in accordance with the decision of the doctorate board of this university, I, George Atsopardi, confer you, Stephen Ndung'u Macheto, the title of doctor and all the rights associated by Dutch law or custom with a PhD degree at the University of Groningen. Do you, as a doctor, promise to act in accordance with the Netherlands Code of Conduct for Research Integrity 2018 of the Universities of the Netherlands, both now and in the future?
Yes, I promise.
Now that I have performed this task assigned to me, let me be the first to congratulate you on your PhD degree and to address you as doctor.
As proof of this PhD degree, I will present you with this certificate signed by the Rector Magnificus, the Secretary and Supervisors, and sealed with the Great Seal of the University. But before doing so, very learned scholar, Dr. Macheto, it is my pleasant duty to congratulate you also on behalf of the doctorate board of this university on the degree that you have been awarded. So before closing the ceremony, all the online participants, thank you very much for all your help and questions that you asked today. Groningen is not only an online place, it really exists. So we hope to be able to see you here in the flesh at some point, whether coming from Spain or from Stellenbosch. And I now declare this ceremony closed.